Section 2.3, the title is Rational Functions, and hopefully this will more or less be a review for some of you in that we covered rational functions in intermediate algebra. Rational functions were the functions that had vertical and horizontal asymptotes. So for instance, the graph of a function could look something like this, where we had the dashed lines, vertical lines, and then maybe we had a dashed horizontal line, and these were more or less boundaries for our function. And so we would have curves that came in and would approach these asymptotes but never actually cross them. Perhaps we'd have a little piece in the center that sort of looked like a parabola but wasn't actually a parabola. And then we'd have a piece off to the side. And we've seen these in the earlier sections. But just to give you an idea of what type of functions we're talking about, there's the graph of one. And so it's somewhat convenient that we introduce rational functions after section 2.2 now that we know what polynomials are. A rational function is defined as a polynomial p divided by another polynomial q, where p and q are polynomials, and so in other words we only have positive whole number exponents for our variables. So we have a remark here that simply states we're not going to consider p or q or other polynomials that are relatively prime to form our rational function, which is basically a fraction that involves polynomials in the numerator and denominator. So here's an example of one that we're not going to consider, and I'll just call it f of x as we usually do. But for instance, if we had the polynomial x minus 1 on the top times x plus 2, and then on the bottom we had an x minus 1 again, and perhaps x plus 3. So if we factor the polynomials, they will not have common factors like the x minus 1 here. So we don't consider these. And as always, example 1, first example of the section, we just want to start out by identifying what's a rational function and what's not. Well, we're simply carrying forward what we learned in section 2.2. We want to look at the numerator and the denominator. If both of them are considered polynomials, then we're good to go. F of x, is it a polynomial? Well, let's look at the numerator. Exponent of this variable is 1, and then we just have a constant here, and so we can interpret that as having an exponent of 0. So 1 and 0, positive whole numbers. On the bottom we have 2, 1, and 0 again. So all positive whole number exponents, f of x is a rational function. G of x is a rational function. P of x can also be considered a rational function, because on the bottom we could say that, well, our polynomial is just a number, it's 1. And the exponent is of the variable is 0. Again, whole number exponents. And I guess I should be careful. I shouldn't say that we have positive whole numbers, because 0 is neither positive or negative. It's neutral. But for p of x, it's pretty much the same explanation as we had in intro for numbers such as 5. We said 5 was a rational number because we could write it as 5 over 1. And a rational number is simply a number that can be expressed as a fraction with integers on the top, the numerator, and the bottom, denominator. Same reasoning here for little p of x. T of x we could look at as a 37 over 1. And if you just have to have a variable written, then we could call this x to the 0 on the top and the bottom. So capital T of x is a rational function. H of x is a rational function. Here we have capital R. We want to check each exponent. So 4 is a whole number, 5 is a whole number, 3. Here we have a 1. There we have a 2, and then here we have a 0, so that works. I'll put checks on the other ones. Okay, what about the bottom? Well, whole number exponent, whole number exponent, and again we have a constant term in the expression on the bottom, which can be viewed as the number times x to the 0 whole number. So capital R of x is overall a rational function. L of x, rational, and many more. So I suppose we weren't actually picking them out. It just said that all of these are rational functions. So I guess I'm guilty of not actually reading the instructions. So let's look at example 2. Example 2 reads, for the rational functions f and g, and we can check and verify that they are rational. The numerator is a polynomial, and so is the denominator. And I'll move this down a little bit. G of x, whole number exponents for the numerator and denominator polynomials. So they are both rational functions. And once again, what will we do without these problems where we just simply evaluate the function and the number inside? Okay, we want to put in a -2 into f. So we have -2 squared minus 1 on top, and then a -2 squared on the bottom, plus 8. Well, we get a 4 minus 1 on the top. -2 squared is a positive 4. Same for the bottom denominator, except we add 8. And we end up with 3 on the top, 12 on the bottom. That fraction can be simplified as a 1 over 4. So f of -2 is 1/4. Well, here we go with a decimal number. We're dealing with f again, and so we have a -1.5 squared on both the top and the bottom. We square the negative, so these will both result in a positive 2.25. We subtract, we add, and we get 1.25 divided by 10.25. I suppose we could simplify that, but I won't bother. This would be our y for x equal -1.5. You just simply put it in your calculator if you want to do better than that. G of 3, new function. We now have 2 minus 3x on the top, so I write 2 minus 3 times 3, being given the number 3 inside the function notation. And below we have 2x plus 5, so instead we write 2 times 3 plus 5. 2 minus 9, 3 times 3 is 9, and then 2 times 3 is 6 on the bottom, plus 5. 2 minus 9 is a -7, and we have an 11 on the bottom. And this can't be simplified. It's best just to leave it the way it is. It gives us the exact answer. G of -3/2. Gonna make some room here. Well, negative 3 halves is the same as a negative 1.5. So we have 2 minus 2 minus 3 times a negative 1.5, and negative 3 halves is negative 1.5. So you can write either one. And then a negative 1.5 on the bottom multiplied by 2 and plus 5. Minus 3 times minus 1.5 would result in a positive number, so we'll add instead. And 3 times 1.5 is a 4.5. 2 times a negative 1.5 is minus 3, plus 5 on the bottom. 2 plus 4.5 is 6.5. On the bottom we have 2. And so 6 divided by 2 would be 3, and a 0.5 divided by 2 would be 0.25. So this could be written as 3.25. G of negative 3 halves is 3.25. Alright, well, an old question, what is the domain? And this was one of our standard examples of a function that restricts the domain through the denominator, in that we do not want q of x, whatever polynomial, whatever name it is, it could be f or t or q, whatever polynomial we have on the bottom, we do not want that to be 0. Okay, because if we divide by 0, it doesn't matter what we have on the top. We're going to get an error in our calculator, or more mathematically, we're either going to get some number non-zero divided by 0 would be undefined, or 0 divided by 0 indeterminate. So we don't want this to happen. Alright, so what we do is we take q of x, and we can say does not equal 0 or set it equal to 0. We want to find the x values that cause this polynomial on the bottom in the denominator to become 0. So I can explain this till I'm blue in the face, but there's no better way to learn than to see an example. So here we have little f. Well, what is the domain of little f? Well, it is a rational function, so automatically you want to focus on the denominator and say, what causes the denominator, x minus 3, to be 0? So we set it equal to 0, we solve the equation that we get, and we see that this causes the denominator to be 0. So we exclude this number, or this value, from the domain. Any other number we are happy with. So how do you write that? We simply take all real numbers and we stop the intervals at 3. So we write 3 parentheses union, pick it back up immediately after 3, and then we continue out through the positive numbers to positive infinity. So this is our domain. This is a list of all the x values that I can put into this function and get a real number back. I can get a y that is a real number, and f of x is our output. Y is our output. So inputs, these guarantee that I get a real output y. Alright, so to put it in simplest terms, we're just taking the denominator and setting it equal to 0. As a whole, for part B, this is our polynomial in the denominator, but we were given a break and it's already factored for us. So when I take the polynomial and set it equal to 0, this is going to break up into two separate equations, to where if x minus 2 is 0, then we'd have 0 times whatever number this became, and we'd end up with a 0 in the denominator. We don't want that. Or we could have 3x plus 7 equals 0, and we get the same result. So two more simple equations. We want to exclude x equal 2 from the domain, and when we solve this equation, it tells us that we do not want negative 7 over 3 to be in the domain either. So we say exclude from domain. Another way of saying it is just to say all real numbers in the domain except for 2 and negative 7 over 3. So as usual, I will write this in interval notation. Negative infinity. And then if you look on the top, this is polynomial. If this is a rational function, then we have a polynomial here. And so the polynomial in the numerator is not going to restrict the domain ever, because domain of a polynomial is all real numbers. So the only thing that restricts the domain for a rational function is the denominator. So we start at negative infinity. Which number will we run into first? That would be the negative one. So we skip it, and we show that like this. That doesn't look like a negative 7, so I'll rewrite it. And now we have another number that we have to skip. So I go from negative 7 over 3 to a 2. And I skip 2, and then from 2 out to infinity. So this is what we were looking for in part B. Part C, we have a function called g. And once again, you probably noticed that you could factor the top and the bottom, but that's not necessary, because we were already told that they're not going to have common factors. So we'll just worry about the denominator as we have for the other examples. X squared minus 2x minus 3 equals 0. Likewise, you could also say, well, we don't want this to be 0, so you could put a does not equal sign. So if we don't want this to be 0, then we don't want either of these factors to be 0, and our factors would be minus 3 and plus 1. Negative 3 times 1 is negative 3, and then if we add negative 3 and a 1, we get a negative 2. Same procedure that we followed in the previous example. Now that we have factors, each factor is going to separate into its own equation. And I suppose I should bring down a does not equal, because that's the symbol that I used to start with. So in other words, if we do not want this polynomial to be 0, does not equal, then I do not want x to be 3. Likewise, I do not want this factor x plus 1 to be 0, so I do not want x to be a negative 1. So this is do not equal sign is just another way of saying to exclude these from the x values. The domain is going to look like the same format as the previous one. We have two numbers that we want to skip, so we're going to have to use 3 sets of parentheses. We're going to start and end with negative and positive infinity. The first number from the left, or the smallest numbers from the left to right, the first one we would run into is this negative 1. So I skip negative 1 first. And then I want to include the numbers in between negative 1 and 3. But then I want to skip 3 itself. So everything less than negative 1, everything greater than 3, and then everything in between these two numbers, negative 1 and 3. So here's our domain. We could write this as D sub G. And this is our set of x values. Alright. So that completes example 3. We'll scroll on down the page. And now we want to talk about the y-intercept of the rational functions. Well, it's the same as all other functions, whether it's rational or polynomial or whatever. If you want to find the y-intercept, then you simply set x equal to 0, which is exactly what this is saying. We have a function f. What's its y-intercept? Well, we evaluate it at x equals 0, and therefore we have to put 0 in the polynomial on top and 0 in the polynomial on the bottom. It is possible for a y or a rational function to not have a y-intercept. So let's work some examples. Find the y-intercepts of the following functions, g and f. So I write g of 0. On the top, that gives me 4 times 0 minus 5, and 2 times 0 plus 3 on the bottom. And so I actually get a number out, and that means that I cross my y-axis at these coordinates, 0, negative 5 over 3. Alright, cross y-axis right there, these coordinates. So what about f? F of 0 minus 3 times 0 minus 5, and then 0 squared plus 4 times 0 minus 1. Well, any term that has an x is basically going to get knocked out when I put in x equals 0. So we're just simply going to get the constants left over and divide the two, which is a negative 5 over a negative 1, or in simplest terms, a plus 5. So the coordinates for this y-intercept would be 0, 5. Well, what about the x-intercept? So before moving on to the next page, we'll read just a little bit about x-intercepts. It says pretty much the converse of, well, maybe not the converse, but the opposite of what we do for the x-intercept. So find x-intercept. What do? We set y equal to 0. Alright, well that's the equivalent of taking our rational function and we've called the polynomial on top p and the one on the bottom q. So this is f as a whole, this entire fraction. And it tells us that in order to do this, we simply need to take the numerator and set it equal to 0. Which makes sense. If we find the number x that makes the numerator equal to 0, then we're simply going to have 0 divided by some different number that q of x is going to give us. Maybe, say, q of x gives us 5. They're different polynomials. They'll give us more than likely different values. So if the top is 0, then 0 divided by a non-zero number is going to give us 0, which is the equivalent of taking the entire rational function and setting it equal to 0. So to do this, all we have to do is take the numerator and set it equal to 0. Alright. So if that doesn't make any sense, you'll see what I'm talking about shortly with example 5. Okay. Oh, I don't know how. There we go. Example 5. This is a good example because you run into a weird situation. I just said take the numerator and set it equal to 0. Set numerator or the polynomial on top equal to 0. Well, if you do that with little f of x, you just take the numerator 7 and you set it equal to 0, and this is not true. This is false. And in more practical terms, that means that f of x has no x-intercept. So we actually like these situations, which this would probably make it harder to graph with no points to be plotted. But what about g of x? X squared minus 25 equals 0. This is the numerator. We don't worry about this bottom polynomial. Top, set it equal to 0. Add 25 to both sides. 25 becomes positive, now on the right side. And according to the square root property, we can just simply take square root of both sides. Remember to put your plus or minus in front of the radical. And so now we can write x equals plus or minus square root of 25 is 5. So here are our x-intercepts. If we wanted to write those as coordinates, we would say -5, 0, and 5, 0. What about h of x? A little crazier polynomial on the top. Luckily it doesn't have a constant term, or else we'd pretty much just have to rely on our calculator. Numerator equals 0. Well, with no constant term, we can factor an x out of each term. So already we can say x equals 0 is an x-intercept, but we'll go a step further and factor this part, which is necessary. One times a -2 gives me this -2, and then 1 plus a -2 gives me the -1b. So what this tells me is that I have three x-intercepts. X equals 0. We just simply take each of the three factors and set it equal to 0. X minus 2 is going to result in x equals 2. And x plus 1 is going to result in the 0, x equals negative 1. Alright, so if you took intermediate, you pretty much learned how to do all of the hard part. And like I said, this is more or less a review of intermediate algebra. Hardest part is knowing how to factor. And even if you can't factor, you can fall back on the calculator, or you can fall back on the quadratic formula. Okay, isotope. Basically sort of a boundary. And there's different types of asymptotes. We are only going to talk about horizontal and vertical, as we did in intermediate. But if you look at these graphs below, here we have what looks like a parabolic isotope. Okay. Here, this is definitely not completely horizontal or vertical. So this is a vertical asymptote, this dashed line that runs from top to bottom. But this asymptote is a slant. I'll go back and call this parabolic asymptote. And I always leave out my P. Hopefully that doesn't bother you. This one points out an important property of horizontal asymptotes. They can be crossed. They're not like the vertical asymptotes. Vertical asymptotes are never crossed by the rational functions. However, the horizontal ones can be. They just simply have the property that as x approaches positive infinity or negative infinity, then the rational function is simply going to start to approach the horizontal asymptote, get closer and closer and closer, but at the far left and right, negative and positive infinity, the function will not cross. However, somewhere in between it may or may not. So this is a horizontal asymptote. Here is what looks like, what is this? Exponential function. And we'll talk about that in a later chapter, but it also has a horizontal asymptote. As this function travels towards negative infinity, it gets closer and closer to this value of y equal negative 3, but it will never cross it. It'll just simply get closer and closer. And the last one is one of the types that we will look at in this section. We just simply have a horizontal asymptote and a vertical one. Alright. Asymptotes of a function give information about the end behavior of the function. Alright. Remark 4, all rational functions except polynomials have asymptotes. The type of asymptote of a rational function depends on the degrees of the polynomial on top and the one on bottom. And so here it reminds you that we're only going to look at these types, vertical and horizontal, not the slant or the other types of curves. Okay, and what it means here by except polynomials, if we just simply have some polynomial or rational function where we can write it as p of x on top, polynomial on the top, but then we just simply have some constant on the bottom. It could be 1 or it could be 2. This isn't going to have a isotope whatsoever. Alright. Definition 3, x equals a is a vertical asymptote of the function if, as x approaches a from left to right, the value of f of x approaches positive or negative infinity. And so if we look at this graph below, here is our vertical asymptote, this vertical dashed line. And as you see the curve here, as it gets closer, if we go from right to left, as it gets closer to x equal a, it shoots up, it skyrockets to infinity. Okay, and likewise, this piece on the left, as we approach the vertical asymptote from the left, it shoots down to negative infinity. Alright. B, the line y equals b, whatever this value is, it looks like y equals 2, so b is 2. Horizontal asymptote of a function as it approaches plus or minus the value of f of x approaches b. So, in other words, this curve, if I was to extend this, and it's hard to draw it because this is already really close to y equal 2. This is going to get closer and closer and closer as it moves out to infinity, but it's never going to cross it, and it's never going to reach 2 exactly. Likewise, over here, it's just simply coming from the top instead of the bottom. It's going to get closer and closer to y equal 2. So how do we find the vertical asymptotes? Well, it's the same way that we found the numbers that were excluded from the domain. In a nutshell, we set the denominator equal, not equal, to 0. Okay. Remark 6. The domain of a rational function consists of segments of the x-axis separated by the vertical asymptotes. Okay, we exclude these x values that make the denominator 0. Hence, one can find the domain of vertical asymptotes by just simply taking the bottom polynomial and setting it equal to 0. Okay. Example 6 reads, find and draw the vertical asymptotes. Do not graph the function. Also mark the domain of the function on the x-axis. Okay. A, little f, x minus 4 equals 0. Add 4 to both sides. This is the location of vertical asymptote. Alright, so we go to x equal 4 and we draw a vertical dashed line. Mark the domain of the function on the x-axis. We could do that by putting an open dot here on the x-axis and then shading the entire number line to the left, and then shading the number line, to the right and to the left. 4 is the only one excluded from the domain. How about G? Set it equal to 0. Factor the quadratic function. Negative 3 times 2 is negative 6. Add the two numbers together, you get the negative 1 in the middle. So this translates to 3 and negative 2 being the vertical asymptotes. X equal 3, x equal negative 2 are vertical asymptotes. So we find x equal 3. we draw a vertical dash line at that location, -2, same drill, there they are. Now we want to mark the domains. I'll put an open dot both of these locations and simply shade and put arrows on the ends of the part of the x-axis that is in the domain. And don't forget to shade in between the two if you have more than one. H of x, all of our works, the hard work is done for us. This one results in x equal 2. This one would give us x equal -1/2, and that factor would result in x equal 3. So it's already factored. We just take each factor and set it equal to 0 and solve the equation. We'll get 2, -1/2, and a +3. So now we have 3 vertical asymptotes. And so I find these locations on the x-axis. I put a vertical dash line for each one. X equal a -1/2, x equal 2, and now 1 for 3. So the domain will not include these values, so I put open dots there and I shade in between on the left and right. Put arrows on the left and right far ends and shade in between. So these are the x values that are permissible for the domain, and open dots for the values that are excluded. -1/2, 2, and 3 are excluded from the domain. D, good example here. Denominator is x squared plus 9 equals 0. We can solve this for x, and we would get x squared equal -9. Square root property says that we take the square root of each side, and on the right we put plus or minus in front of it. This results in x equals plus a square root of a -9 or negative square root of a -9, either one, plus or minus. And with the negative inside the square root, I replace that with an I. So in other words, I have two complex numbers for the vertical asymptotes, and those are not located on the x-axis. X-axis only contains real numbers, and I don't really need the square root anymore because square root of 9 is 3. So let me fix this. Each one would definitely have an I because of these negatives inside the square root. So this one would be 3i. This one would be a negative because of the negative on the outside, -3, and then an I for the negative inside. These numbers are complex. They're not on the x-axis. So we would say no vertical asymptotes. And so I finally put the P there. Finding the horizontal asymptotes, probably the worst part about graphing a rational function, because we have these rules that we need to memorize, and I'm not all that great at memorizing things. Pretty good at memorizing procedures, but not just rules. I sometimes get these confused, but they're easily understood. We've got P is the polynomial on top and Q is the one on the bottom. And earlier we said that the horizontal asymptote locations depend on the degrees of the polynomials. So first situation, if the degree of p on the top is less than the degree on the bottom, if the largest exponent on the bottom, or sorry, if the largest exponent on the top is smaller than the largest exponent on the bottom, then we just simply say there's no calculation to do. If we confirm this fact, then we say that the horizontal asymptote is the x-axis, y equals 0. B, the second situation that we're going to consider, if the largest exponent on top and bottom are equal, then we take the ratio of the leading coefficients, and so we take leading coefficient on the top divided by the leading coefficient on the bottom, and that's where our horizontal asymptote is. So y is going to look something like this. Some number a on top and some number b on the bottom. It's going to be a fraction. Alright, and don't read any more into a and b other than we've got a number that we're dividing by another number. So the point is, it's not simply just going to be 0 anymore if the degrees are equal. And then the last situation, if degree on the top is bigger than the polynomial degree on the bottom, we have no horizontal asymptotes. In this case, it is slant, parabolic, or some other type. And we're not going to consider the situation described in C. So college algebra isn't completely evil. They cut us a break there. Example 7. Draw the horizontal asymptotes. Do not graph the functions. Alright. So, what's the degree? This is the question now. We're not setting anything equal to 0. Degree on the top is 2. And now the degree of the denominator, I should say, equals 2. Where did I get those numbers? Here and here. They're the largest exponent of the variables. Alright, well, how do they compare? Well, degree of the numerator equals the degree of the denominator. This falls into the category, the second one. In other words, this tells us that y equals the location of our horizontal asymptote equals the coefficients, the leading ones, of the numerator divided by the denominator. So 3 over 4. And where's 3/4? Well, I'll say 1, 2, 3, 4. I'll say that this marks the location of 1, and so 3/4 positive would be right here. If I were graphing this rational function, one of the first things I would do is mark this location with a horizontal dashed line. So this is the horizontal asymptote. Alright. What about little r? We have degree of numerator. How do they compare? I'm going to put a symbol in between here. Are they equal? Is one greater than the other one? Greater than? Less than? What's the deal? Denominator. Alright. So I'll find these. This is 1. That will go right here in between the box. And here is the degree of the denominator, and that will go there. How do they compare? Well, numerator is less than denominator, which implies that y equals 0 is the horizontal asymptote. And where is that? Well, that's just simply the x-axis. And most of the time, you don't want to just simply um, trace over the x-axis. Sometimes you can't even see it, depending on your pencil. But I usually go to the x-axis and I put dashed marks off to the left and the far right of the x-axis. So here is our vertical isotope, or I'm sorry, not vertical, but horizontal isotope there. So my graph usually looks like this: dashed on the sides, dash, 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 dash. All right. Q, well, doesn't look like we have a coordinate system here. And I don't think we're going to need one. So box, degree of numerator, degree of denominator. Let's find them. Top numerator is degree 2 and the bottom is 1. So now we have the top is greater than the bottom. So it says that this does not have a horizontal isotope, but that does not mean that it doesn't have a horizontal, or I'm sorry, an isotope at all. It could have some other type, but we're not going to graph these type. So we could say no horizontal isotope, but it could have some other type, or it may not have one at all. So now we're going to get into graphing rational functions.